Welcome everyone. In this video lecture, I will discuss about oscillations and waves. So, the basic question is, what do we mean by oscillations and waves and why we need to study this? Oscillation is the repeated variation, typically in time, of some measure about a central value or between two or more different states. So now, if we consider vibration as the oscillation, the term vibration is precisely used to describe mechanical oscillation. For instance, a swinging pendulum and alternating current. Nevertheless, oscillations occur not only in mechanical systems but also in dynamical systems in virtually every area of science. For example, the beating of the human heart, electronic oscillator, tuning fork, periodic firing of the nerve cells in the brain, business cycles in economics which actually goes up and down, geothermal geysers in geology, vibration of strings in guitar or other string instruments. So now, what is a wave? A wave is basically a disturbance of one or more fields such that the field values oscillate repeatedly about a stable equilibrium value. Stable equilibrium means the stable resting position. Disturbance means the change from the equilibrium. The simple example is the surface waves in water swing water ripples. There are other examples such as sound waves. Examples of mechanical waves are seismic waves, gravity waves, shock wave. A shock wave is a type of propagating disturbance. This figure is the first Solarian photography of shock waves interacting between two aircraft taken by NASA in 2019. Solarian photography is basically a visual process that is used to photograph the flow of fluids of varying density, and it is widely used in aeronautical engineering. And this one is a two-dimensional representation of gravitational waves generated by true neutron stars. So what we see here that the vibrations and the waves lie at the heart of many branches of science and engineering. Therefore, we need to study and understand the concepts of oscillations and waves. Here we will cover simple harmonic motion, mathematical representation of simple harmonic motion, the simple pendulum, energy in simple harmonic motion, damped oscillations, and forced oscillation. In this part, I will discuss the simple harmonic motion and the mathematical representation of simple harmonic motion. Now, before discussing about simple harmonic motion, we need to know the concept of periodic motion, a special type of motion called periodic motion. It is a repeating motion of an object in which the object continues to return to its given position after a fixed time interval. For instance, a pendulum and the spring mass system. So, we will focus our attention on a special case of periodic motion which is called simple harmonic motion. We shall find that all the periodic motions can be modeled as combinations of simple harmonic motions. Therefore, simple harmonic motion forms a basic building block for more complicated periodic motion. Basically, if we understand one type of harmonic oscillator, then we can readily understand and analyze many other types. The universal importance of simple harmonic motion is that basically to a good approximation of many real oscillating systems behave like simple harmonic oscillators when they undergo oscillations of small amplitude. Accordingly, the elegant mathematical description that we will develop can be applied to a wide range of physical systems. Now, our first example of a simple harmonic oscillator is a mass on a horizontal spring, as you can see here. The mass is attached to one end of the spring while the other end is held fixed. If this object vibrates or oscillates back and forth about the same path, each cycle taking the same amount of time, the motion is called periodic. The equilibrium position corresponds to the stable resting position or the unstretched length of the spring, and we denote x as the displacement of the mass from the equilibrium position along the x-axis. So here the system is in equilibrium, and this too actually represents the situation where the system displaced from equilibrium. So when the spring is extended, that is the displacement is positive, the force acts in the opposite direction to the displacement to pull the mass back to the equilibrium position. Similarly, when the spring is compressed, that is the displacement is negative, the force again acts in the opposite direction to the displacement to push the mass back to the equilibrium position. So now there are a few important terms involved in the simple harmonic motion. So displacement is measured from the equilibrium point. Amplitude is the maximum displacement. A cycle is a full to and fro motion, and this figure actually shows the half a cycle. Period is the time required to complete one cycle, and the frequency is the number of cycles completed per second. So here we are starting with an idealized version of a real situation. It is idealized because the mass is assumed to move on a frictionless surface, and we assumed that the spring has no mass. Moreover, as we are considering the motion in the horizontal direction, we are not considering any effect due to gravity. In physics, it is quite usual to start with a simplified model, as the real physical situations are normally very complicated and not easy to handle. So the simplification actually makes the problem manageable so that an initial and idealized solution can be obtained. The complications, for instance, the effect of the friction on the motion of the oscillator can be added, and at each stage a modified and improved solution can be obtained. This actually provides us the basic building block for more complicated periodic motion. The force applied by the spring depends on the displacement. So we can write here F is equals to minus kx. So the minus sign of the force indicates that it is a restoring force. It is directed to restore the mass to its equilibrium position, and k is the spring constant. So now if we want to know the definition of simple harmonic motion, so any vibrating system where the restoring force is proportional to the negative of the displacement is in simple harmonic motion and is often called a simple harmonic oscillator. Now applying Newton's second law, that is F is equals to m into a, where m is the mass and a is the acceleration. So if we combine the previous expression or the previous equation, that is F is equals to minus kx, and the Newton's second law, we will get minus kx is equals to m into a. So we can get acceleration a is equals to minus kx divided by m. X is actually the displacement from the equilibrium position. So an object moves with simple harmonic motion whenever its acceleration is proportional to its position and is oppositely directed to the displacement from the equilibrium. Now we know that the acceleration is the first derivative of the velocity with respect to time, or we can say that acceleration is equals to the second derivative of the displacement with respect to the time, and we have this as a is equals to minus kx divided by m. And if we combine these two, we will get d2x by dt2 is equals to minus k by m into x. Now considering that k by m is equals to omega square, where omega is the angular frequency of the oscillator, so we can get this equation as d2x by dt2 is equals to minus omega square into x. So this is actually the differential equation of simple harmonic motion. This equation is the equation of simple harmonic motion, and all simple harmonic oscillators have an equation of this form. It is a linear second order differential equation. Why linear? Because each term is proportional to the displacement, that is x or one of its derivatives. And second order because the highest derivative is second order. So the mathematical solution of this equation is a function of t, and this is equals to a cos omega t plus phi, where a, omega and phi are constants. So this is actually the graphical representation of x is equals to a cos omega t plus phi. We can say that this motion, that is the motion of an object in simple harmonic motion, is sinusoidal. So what do we mean by that? we mean that the values like displacement, velocity and the acceleration vary in the shape of a sine and cosine curve. This is the equilibrium point. It is the amplitude. Basically is the height from the central line to the peak. Or we can measure the height from highest to lowest point and divide that by 2. And this is the period, which is actually the time required to complete one full cycle. Now we can know that the time period is equals to 2 pi divided by omega, and we know that omega is equals to root over k by m, so we can write this time period is equals to 2 pi into root over m divided by k, and we can write the frequency in this form. Now to describe the harmonic oscillator, we need to get the expressions for displacement, velocity and acceleration as function of time. That is, you can say as x as a function of t, v as a function of t and a as a function of t. So x as a function of t is basically the displacement, v as a function of t is the velocity and a is a function of t is basically the acceleration. So x is equals to a cos omega t plus phi. V velocity is the first derivative of the displacement with respect to time, so we can get this as minus omega into a sine omega t plus phi, and a is the acceleration, that is the first derivative of the velocity with respect to time, or we can say this is the second derivative of the displacement with respect to time. And if you do this derivative, you can get as this is equals to minus omega square into a cos omega t plus phi. So these are the graphical representation of x, that is the displacement, velocity and the acceleration. So this first one is for the displacement, and this is for the velocity, and this is actually for the acceleration. So you can see here that when the displacement is actually 0, you can get the velocity as maximum, and at that point the acceleration is basically 0. And at the same time, when the displacement is maximum, you can get the velocity as 0 and you will get the maximum acceleration. So from the expression of velocity, we can estimate the maximum velocity. So we can get the maximum velocity when this sine term will be equals to 1. So that means when this sine term or sine omega t plus phi will be equals to 1, then we will get only this omega into a part. So the maximum velocity is equals to omega into a, and we know that omega is equals to root over k by m, so we will get this as root over k by m into a. A is the amplitude. So now from the expression of acceleration, we can get the maximum value of the acceleration when this cos term will be equals to 1. So that means the maximum acceleration value will be equals to omega square into a, and that will be equals to k divided by m into a. Now before summarizing this part, let's talk about the application of simple harmonic motion. An application of simple harmonic motion is to keep track of time. Here the motion is periodic and each oscillation takes the same amount of time to complete. So clocks can use the oscillations to keep track of time. The simple example is the grandfather clock or the pendulum clock. The simple harmonic motion of a swinging pendulum is used to keep track of time. Now to summarize, you have learned here the simple harmonic motion and its mathematical representation. Basically, the following equations form the basis of the mathematical representation of simple harmonic motion. So we started with f is equals to minus k into x. Then we use Newton's law, and when we combine these two, we get this expression as the second derivative of the displacement with respect to time, which is equals to minus omega square into x. And we find solution as x, which is a function of t, is equals to a into cos omega t plus phi. And we learned the graphical representation of this solution and also some useful terms like the period and the frequency.